For us here, Chapter 19 deals with another kind of equilibrium, and is one called Ksp. So we want to talk about, first off, what are the equations we're talking about when we see a Ksp, because whenever we see a K, that implies a certain chemical equation, and it's different for Ksp than it has been for Ka or Kb or just plain old Keq. We want to look at our Ksp expression. It's a slightly different than ones we've seen before. And the big thing is we want to define this idea of solubility, which is how concentrated a solution can we make. And we're going to make a relationship here between Ksp and solubility. So these are the four things we want to try to accomplish in the next few minutes. When we were talking early on about whether something is going to dissolve or not, then we learned our solubility rules. And our solubility rules, we said something like magnesium ions and hydroxide ions. If those go together, they form magnesium hydroxide. And from our solubility rules, we know that hydroxides just are not very soluble. Most hydroxides are insoluble, except for the alkali metals and calcium, barium, and strontium, which are relatively soluble. But if we test our magnesium hydroxide, which is Phillips milk of magnesia, then we find out that it does conduct a little bit. Okay, it's not a great conductor, it's a weak electrolyte, but it does conduct, shown here by this little light bulb. It's a neon glow bulb, and that this does light up. So we know inside our solution there are some magnesium ions and there are some hydroxide ions that are floating around and able to conduct electricity. So we have to sort of change our idea of precipitates, and we're not going to say that when we have a compound that's a precipitate that it does not dissolve at all. We're just going to say that it has low solubility and that in that solution there are going to be some molecules that have dissolved. Some of this compound is going to have dissolved into ions. Now the kind of equations we're going to see for this are things like, a solid, like a silver chloride. We've learned that that's a precipitate, silver chloride, but it does break up a little bit to give silver ions and chloride ions. In the same way, our lead iodide, is a precipitate, but it does break up a little bit to give some lead ions and some iodide ions. And the same thing here with our aluminum hydroxide. We learned that hydroxides are pretty much not usually very soluble, but they do break up a little bit to give us, let's say, aluminums and hydroxides. So we would go back now and say, well, what is our Ksp expression for this? And this just follows the rules we've seen before. Now we say the K is the concentration of our reactants over the products raised to the power of their coefficients. So this would be Ag plus times the concentration of Cl minus. But we're not going to put it over anything because what we have here is a solid, and we know that solids do not enter into our K expression. So this special case is called Ksp, and that means a solubility product, because we're talking about solubility, things dissolving a little bit, and product is when we have two things multiplied together. So here we have silver times chloride concentrations, so the result of a multiplication problem is always called a product. So solubility product. For the lead iodide, we'd have a Ksp, and that would be lead, Pb2+, concentration of lead, times the concentration of iodide squared. And again, there's no denominator, but it exactly follows our rules, but it's a little odd looking because, there is no denominator in these guys. Okay, the last one here, to say the aluminum hydroxide, that would be the concentration of aluminum times the concentration of hydroxide, and this time it would be cubed. So in one case it would be a silver chloride, lead iodide squared, and aluminum hydroxide cubed. And this would be writing the Ksp expression. Pretty easy stuff. Now, if we want to look at this a little more closely, we'd say here is our silver chloride equation. We have drawn my icebox and I've rewritten my Ksp. So let's go back and we say, well, if I want to fill in this ice box, I don't really use that set of boxes because it's a solid and that doesn't enter into my equation. However, at this point, I do want to define something called solubility. And for this, I'm going to use S for solubility. Seems reasonable. And what happens here, this is the most concentrated solution of silver chloride that I can make. Now we say we can't get very much of it dissolved. It's going to be a tiny number, but it is measurable. So I'm going to say S over here in this box. S is the amount of silver chloride that will dissolve. And if it does dissolve, that means when I get to equilibrium, it's all gone. Alrighty, so I'm saying just if I had a glass or a beaker of water, and I just put a little speck of silver chloride in, the amount that would dissolve, I'm going to call that S, my solubility. So my change here will be minus S. And if I continue on, my silver and my chloride originally are 0 molar. And if I have taken away S of silver chloride, then I must have made S amounts of silver and S of my chloride, because if the silver chloride dissolves, I get silver ions and chloride ions. So we can see at equilibrium that these two values here are going to be S. Now I'll go over to my Ksp expression. This is going to be S. This will also be S. So we can see we're going to get an expression that Ksp is equal to S squared. Now this is very useful. What this says is if I know my Ksp, I can calculate what my solubility is going to be, or if I could measure my solubility, then I could figure out what my Ksp is going to be. Now notice that this S represents the concentration of silver chloride, but it would also represent the silver ion or the chloride ion. So if I had a problem that said, we found out that the chloride ion concentration in this solution was 1 × 10⁻⁵ molar, then we could put that in, we'd square that, that would be our solubility, and we could figure out our Ksp. And the same thing with the silver ion. Looking back here at our lead iodide example, okay, same situation. We're not going to use this box, because the numbers don't enter into our expression, but we are going to use this for our solubility. And so starting here with 0 molar of our ions, because we just have a glass of, or there's a beaker of beaker of distilled water, and we throw in some lead iodide. Now, if I throw in a bunch of lead iodide, most of it's going to just sink to the bottom, and that's okay. But I'm talking about the amount that does dissolve is my solubility. So again, this is going to be plus S. But what's different here is since I have 2I-, then when I get to this box, it's going to be plus 2S. And that shouldn't be a big surprise. So at equilibrium, this would be S, and this would be 2S. And when I put it into my expression, this is S, and this is 2S squared. So what happens is, the fact that lead iodide is a 1:2 compound actually has a double effect. It gets doubled here, and it gets squared when I put it into my expression. So it gets doubled and squared. So when I'm done, I can see that my Ksp is going to equal 4, because 2 squared is 4, S cubed. So for a 1:2 compound, then this expression comes out to be Ksp equals 4S cubed. And again, that's just as useful as I had before. If I know the Ksp, I can find the solubility. If I know the solubility, I can find the Ksp. And if I knew, let's say, the lead ion concentration, then I know that that's the same as my solubility. If I knew my iodide concentration, I had to be a little careful because that's going to be double my solubility. So I could divide by 2 and then go back and figure out the Ksp. Let's try it again. Here we have our aluminum hydroxide. Again, we don't care about that box, but we're going to use it for our solubility. And we're going to start off here with 0 and 0. This is going to be plus S. This would be plus 3s. And you can probably already see what's going to happen. When we put it into our expression, we have s, and this one is 3s cubed. So like we had before, where it was 2s squared, okay, this guy's going to be 3s cubed, so it gets tripled and cubed. It has a double whammy on that. So when we get done with this guy, we can see we're going to have Ksp is equal to 3 times 3 is 9, times 3 is 27. So 3 cubed is 27. We have s cubed times s, so it's s to the 4th. So Ksp equals 27s to the 4th. So when we get a 1 to 3 compound, and that would also work to a 3 to 1 compound, obviously, then we're going to get Ksp equals 27s to the 4th. If I know the solubility, I can find the Ksp. If I know the Ksp, I can find the solubility. So you can see what happens is if we see a 1 to 3 compound, we have s, and then if we have a 3, then it's 3s, so it's tripled and cubed. So if we had something like, let's say, aluminum sulfide, which is a 2 to 3 compound, then we wouldn't have to do all the work. We could say, okay, this guy is going to be doubled and squared, and this guy is going to be tripled and cubed, and that's going to be 4, and it's 27, so Ksp would equal 108 s to the 5th power. So we don't even have to work out our whole ice blocks. We can kind of figure it out just from each of these little compounds. So here's a little chart that goes back and kind of summarizes all this. If I have a 1-to-1 compound like AgCl, Ksp equals s squared. A 1-to-2 compound, Ksp equals 4s cubed. Okay, 27s to the 4th, and 104. That's not 104, it should be 108. Okay, 108s to the 5th if we have a 2 to 3 compound. Now, if I wanted to do something like, let's say, silver chloride, and I wanted to compare with, let's say, silver bromide, and if I knew the two Ksps, which one is more soluble, well, because these are both 1-to-1 compounds, it'd be very easy, just whichever one has the larger Ksp is more soluble. But if I wanted to compare, let's say, AgCl with PbCl2, okay, now that's a little trickier because this is a 1-to-2 compound, and this is only a 1-to-1 compound, so I would actually have to go back and calculate my solubility in order to say which one is more soluble. So if they're both the same, if they're both 1-to-1s or both 1-to-2s, you can just compare by looking at the Ksp, but if they're in different groups, you have a 1-to-1 versus 1-to-2 or versus 1-to-3, then you really have to go back and calculate the solubility. Okay.